43 of this lecture series on MOSFETs, we derived the small signal model, including the small signal model, we derived the AC equivalent circuit of a common drain circuit or the source followers. Over here, you see this is the gate terminal. Okay, the drain is common. It's a source follower circuit, and this is source. Okay, you can see the difference is over here is the VGS. That's the difference. It's the potential difference between the gate terminal and the source terminal. So this circuit can be derived from, for example, this is a common drain or source follower configuration, in which you see the drain over here, and this consists of the DC sources as well. So when drawing an AC equivalent circuit, you usually kill the DC sources, so you can see the drain is the common signal ground. Okay, so once this is grounded, and this is your gate terminal, then your biasing resistances R1 and R2, they appear as parallel resistances. Okay, so these biasing resistances are these are biasing resistances. Parallel combination of them constitutes the input resistance. Okay, so if we talked earlier in part 44 as well that if the output resistance of the source RSI is small, okay, if it is a low resistance, then the loading effect is small. That means your if you write this V in terms of the voltage divider terms, that is V in can be written as your Ri, which is the Thevenin input impedance of the amplifier, or you can say this is the equivalent Thevenin impedance of resistance of the biasing resistances R1 and R2 in parallel, and your expression for the input voltage over here can be written as Ri over Ri plus RSI into Vi. Okay, into Vi. Now, if you see over here that your input resistance, which is whose values is being dictated by the parallel combination of R1 and R2 over here, is much greater than RSI, then that means the loading effect at the input can be ignored. Okay, the loading effect can be ignored. So that means a very large fraction of Vi is available at the input node, which is the gate terminal over here. Okay, this is the gate terminal, and usually in this building up the AC equivalent small signal circuits, we ignore the capacitive reactance, so it's a short circuit and AC equivalent models. All right. So you see the small signal input resistance Ri is defined in the small signal model. Okay. So for example, the input resistance is the Thevenin equivalent resistance of the bias resistors. Also, we assume that since we have an insulated gate in the MOSFET structure, so we ignore any gate capacitance, so any capacitive reactance of gate is ignored between the metal and the semiconductor substrate. We ignore that capacitance, and there's no Ig, there's no input gate current. So it means that the Ig is 0, so that means the input resistance of the MOSFET device is infinitely high. Okay, so essentially the input resistance of this common drain or source follower configuration, the input resistance, far as input resistance is concerned, it is set by the parallel combination of R1 and R2. Those are the biasing resistances. Okay. You see these resistances are setting up the voltage Vg over here, and that Vg is given by R2 over R1 plus R2 into VDD. Okay, that's the DC Vg. Just like over here, we have a voltage divider expression for the input voltage. Okay, at this node, at the gate node for AC quantity. Right. So even though the input resistance to the gate of the MOSFET is essentially infinite, the input bias resistances do provide a loading effect. Okay, so it depends on how large Ri is compared to RSI. It is a source resistance. If it is large, then you can ignore the loading effect. Okay, so it depends on how much Ri is for that particular settings of the amplifier. So this same effect was also seen in the common source circuits. Okay, so it depends again on the biasing resistances, how large they compare with the source resistance. If RSI is small, well, in both the common source and in the common drain configurations, the loading effect can be minimized. Okay. All right. Now that was for the input resistance. Okay. Now if we have to evaluate the output resistance, then what we do is, the first thing we want to do is You want to kill this input Vi, and instead you apply a voltage at the output, at the source terminal, at the source node, and by the Ohm's law, just simply evaluate the ratio of the output voltage divided by the input current. Okay, so for example over here there is no Vi. Okay, Vi is first set to equal to 0, so Vi is shorted out. Okay, so this is an equivalent circuit for Nmos source follower for determining the output resistance. So over here we are applying a voltage source Vx, then there's a current Ix that is flowing in the source node towards the source node. Okay, so basically your R0, that is the output resistance, is the ratio of Vx by Ix. Okay, so um, that's how you determine the output resistance. Okay, so to calculate the small signal output resistance, we set all the independent small signal sources equal to 0, and we apply a test voltage to the output terminals and measure the test current. Okay, so these are the two things. We need a test voltage and we need a test current. The ratio of that is the output resistance of the common source, of the common drain or the source follower amplifier. So we set the input voltage 0, apply a test voltage Vx. Since there is no capacitance in the circuit, the output impedance is simply the output resistance. Okay, so this is real, this is not capacitive. So this is defined as R0 is Vx by Ix. So writing the KCL equation at the output source terminal, you see, if you write the KCL, for example, this is the same node. Okay, this is the same node. This is actually, these are the source nodes. The drain is common, it's the common ground. This is the gate node. So what you have over here is, if you write KCL at any node over here, for example, you select this node, then Ix is coming into the node. So this is Ix plus you have another this is Ix. Okay, this is the test current Ix plus you have another dependent source, current dependent source, which is dependent on the voltage VGS. So then looking at the direction of the current, this current flows again inside that node. So you have this, you can write this as Ix plus GM VGS considering the same direction. So both currents are coming inside the source node. So this should be equal to, where does this current go? These currents are distributed, they bifurcate themselves into two nodes. So one is your source resistor Rs, the other is the small signal output resistance of the transistor R0. Okay, so we can write this as Vs divided by Rs. Okay, Vs by Rs. Actually, Vs is your Vx, isn't that right? I mean, since we are considering this as Vx, so let's have this as Vx. Vx by Rs plus Vx divided by R0. Okay. So these two currents, this current, and this current, Ix is the test current, they flow in towards the node. Okay, they're flowing in towards the node. And then this is how the current is bifurcated into two resistive branches, okay, which can be written as Vx by Rx and Vx by R0. So we have this expression for out of the KCL equation. It's the same expression. So Ix plus Gm VGS, if you look at the above circuit closely, this is Vx by R0 plus Vx by Rs. Now the other thing to note over here is that since we don't have any Vi is 0. Okay, this is gate terminal, right? So if you look this closely, if you apply KVL at this loop, then that means the sum of all the voltages around the loop should be equal to 0. That means this implies that VGS is equal to, since this and this is what? This is Vx, okay, which is plus minus Vx. So VGS should be equal to minus Vx. Okay. So VGS plus Vx, VGS plus Vx should be equal to 0. That means VGS minus should be equal to minus Vx. That means I can take this Vx on the other side. So what I'm left with over here is, this should imply that Ix can be written as, if I take Gm over here, so Gm plus 1 over R0 plus 1 over Rs, and then I can take Vx out, okay, or I can take Vx on the left hand side of the equation at the denominator position, And this expression is nothing but this is the inverse of the output resistance R naught. So I can write this as R naught inverse. Okay. So you see, well, what you can do is you can write this as 1 over 1 divided by Gm, okay, plus the same terms, plus 1 over R naught plus 1 over Rs. So you see this whole thing has the dimensions of R naught inverse, okay, or if you want to evaluate R naught, then R naught is basically equal to, you take the inverse of both sides. So this means that of these three terms in the denominator, this is parallel combination of these three terms. That means your R naught is nothing but the parallel combination of all these three resistances. That is 1 over Gm. 1 over Gm also has the dimensions of volts per amp. So this is the resistance. Okay. So that means your transconductance parameter is influencing the output resistance very much. Okay, so 1 over Gm is, it can be noted as if you're looking towards the source terminal. Okay, from here you're looking to for the output resistance. For the output resistance, it's not only the R naught and Rs. It's not only the parallel combination of R naught and Rs, but at the source, you have another resistor, which is given by 1 over Gm. Isn't that right? So you have the parallel combination of all these three resistances. Okay, so R naught is in fact parallel combination of 1 over Gm, parallel combination of Rs and R naught. Okay, so 1 over Gm is going to affect your very much the output resistance. Okay, so 1 over Gm, again, it's a strong concept. It's the resistance of the source node or the source terminal. Okay, and then with the parallel combination of external resistance Rs and R naught, which is an inherent parameter of the transistor, you take the parallel combination. This is the output resistance. So what's happening over here is, I mean, the same. Since there is no current in the input portion of the circuit, so we see that VGS is minus Vx, and then you rearrange those terms of the KCL equation. You can write this as R naught inverse. So that means if you want to take inverse over here, then this R naught is a parallel combination of 1 over Gm Rs R naught. So in the small signal model, we see that the voltage VGS is directly across the current source Gm VGS, which means, well, Gm VGS can also be written as VGS divided by 1 by 1 over Gm. So 1 over Gm is your resistance. And where is this resistance? This resistance is at the source. So this means that the effective resistance of the device is 1 over Gm. So the output resistance given by the above equation can therefore be written directly. This result also means that the resistance looking into the source terminal, ignoring R naught, is 1 over Gm as previously noted. Okay. So let's take one example to see how much, practically how much for any common drain configuration or source follower configuration, how much is the output resistance. So the objective, this is example 4.9 from the course text. Okay, so the objective is to calculate the output resistance of the source follower circuit, and we consider the same circuit as we have considered earlier in part 43 of this lecture. So it's figure 26. If you recall, this is figure 26. This is a common drain configuration. This is your drain. The output is being taken from the source. This is gate. Okay, and this is the AC equivalent circuit consisting of the small signal model of the Nmos device. Okay. Okay, so the circuit and the transistor parameters are given in example 4.7. So if you recall, we talked about example 4.7 in part 43. So we had the threshold voltage as 1.5, BDD was given. Okay, RS, for example, is 0.75 Ks, and the conduction parameter is 4 milliamps. So basically, just bring all those parameters over here. In this example 4.9, so for example, over here again, RS is 0.15 Ks. R2 biasing resistance is R1 are given, VDD is 12 volts. Again, the transistor parameters are threshold voltage, the conduction parameters, channel width, modulation parameter is given. So also you assume that the source resistance is 4 kilos. Okay. So uh, again, one thing that you note over here is if you calculate R1 in parallel with R2, so we have done this before as well. This is your input resistance. Okay, this is your input resistance. And if you recall, in example 4.7, uh, in example 4.7, R1 parallel R2, which is parallel combination of 162 and 463, is 120 case. Okay, which is much greater than RSI, which is source resistance equal to 4Ks. Okay, so there is a minimal loading effect at the input. Okay, so let's see what happens at the output. Output resistance in terms of all these parameters, GM was evaluated as 11.3. So if you are going to evaluate this as 1 over GM, 1 over 11.3, RS is 0.75K, R0 is 12.5K. This comes out to be 78.7 ohms, which is much less than R1 parallel R2, which was equal to about 120 kilos. Okay, so that means your common source configuration, this is 120 kilos, if you recall. Yeah, over here. So this is 4.7, 152 parallel 463 is R is 120 kilos. This is my input resistance. The output resistance for this particular configuration turns out to be 78.7, which is very small. That means that the loading effect when the circuit is going to drive the load over here or further electronics, the loading effect at the output is going to be minimum. That means the configuration is an ideal voltage source. This configuration is an ideal voltage source. It's an ideal voltage source. Ideal voltage source. Why it's an ideal voltage source? Well, first of all, its input resistance is large. Okay, so there is, and then you see, since it's a source follower circuit, it follows whatever the voltage or the AC source is available at the gate. Okay, because the input resistance is large, Ri is large as compared to RSI, so there's minimum loading, and Vn is approximately 98 or 99% of Vi, so it's approximately Vi. So that the loading effect due to R1 and R2 is there, but it's small. If R1 and R2 is much greater than RSI, so that means the input is there is present at the gate as it is, and the overall voltage gain of this configuration, if you recall, is about 90% or 86%. Okay, so for this particular configuration, if you recall in 4.7, we evaluated this as 86%, so it's like 90%, okay, or 86%. So the voltage gain is again 86% of what? Vi. Okay, so what's happening is this, that the output voltage that we are going to get, the output AC voltage, is 86% of Vi. Okay, is 86% of Vi. So it's just following the input. It's just following the input, and since the output resistance is small, there won't be any loading effect. There won't be any loading effect. It's just like, since RSI is small, we have a small R0. That means just ideal voltage source. So it's just like a buffer between Vi and V0. Okay, there's no loading if you want to drive further electronics. So these are the advantages of this configuration. It has a small output resistance. Okay, and its output follows the input. So the voltage gain is almost equal to this is very close to unity, right? So the comment is that the output resistance of the source follower circuit is dominated by the transconductance parameter. Also, because the output resistance is very low, the source follower tends to act like an ideal voltage source, which means the output can drive another circuit without significant loading effects. Okay, so these are advantages of the common drain configuration or the source follower. Okay, the output is just going to follow the input, and it's not going to load the further electronics or the load attached to the source follower configuration. So there is no loading at the output. Okay, that's all.